So we're going to begin today kind of picking up where we left off on Wednesday. So remember, Wednesday we ended with this example where we converted between molarity and molality using density by going from molarity to molality. And the key to this problem was right here, converting the liters of solution into kilograms of water. Well, what we're going to find is that in the problem that we're about to do, it's going to be a similar kind of conversion that we are ultimately looking at. In fact, a lot of the calculations are going to look exactly the same. The only difference is the direction that we're going and how we're going to use those numbers. So I have a 1.92 molal solution of iron 3 chloride. That means I have 1.92 moles of iron 3 chloride in every kilogram of water. I'm trying to convert this to molarity, and remember, for molarity, it's going to be moles of iron 3 chloride for every liter of total solution. Now, the liters of solution, we don't know yet. But we do know that we're going to have 1.92 moles of the iron 3 chloride. So numerator stays exactly the same. The denominator is what we have to change. Now here's where we have to, again, think about what that means to be a solution. A solution is the solute, which in this case was the iron 3 chloride, plus the solvent, which is the water. Now we already know the mass of the water. It's 1,000 grams, 1 kilogram. What we need to figure out is what is the mass of the solute. I put those two together, I can get the mass of total solution, and then I can use the density to turn that mass into volume. So again, very similar to the process that we did here. We turned the liters into grams. We subtracted the mass of the solute to get the mass of the solvent, and we converted to kilograms. Here, we're going to add the mass of solute to the mass of solvent, and then convert the kilograms and the grams into liters. So we need to figure out how much does 1.92 moles of iron 3 chloride weigh. That's a relatively simple conversion. We've been doing it since chapter 2. Iron is 55.85 grams per mole. Chlorine is 35.45 grams per mole times 3 of them. 162.20 grams of iron 3 chloride in every mole. Multiply those two numbers together, round to 3 significant figures. I have 311 grams of iron 3 chloride. If I add that to 1,000 grams of water, because again, that's what a kilogram is, that would give me 1,311 grams of solution. Now that I have grams of solution, now I can use density, because this is the density of the solution, to figure out how many milliliters and then how many liters there are. So 1.07 grams per milliliter So 1311 divided by 1.07, rounded to 3 significant figures, would be 1,230 milliliters, which would be 1.23 liters. So the 1.23 liters is what I'm going to insert into my equation for molarity. 1.92 divided by 1.23 to 3 significant figures again gives me a 1.56 molar iron 3 chloride, FeCl3 solution. All right, so when we put it this way, again, the hardest thing about these kinds of conversions is trying to just keep track of what it is that I'm converting and what it is that I'm trying to do. But if you can kind of follow the logic, what I mean by that is that you can kind of see, okay, I have kilograms of one component of the solution. I need to go to liters of all the solution. It kind of falls into place. Okay, these are what my steps have to be. Notice that in each type of conversion, both times, I had to do a conversion between the moles of the solute to grams. And it was the same direction both times. Multiplying that molarity by the molar mass to get the mass of the solute. The only difference was what I did with it. In the first example, I took that mass and I subtracted it from the total mass of solution to give me the mass of the solvent. In this case, I added it to the mass of solvent to give me the total mass of the solution. And then I divided it by the density to give me the volume of that solution. All right, any questions about these conversion types, either direction, before we move on to some other concentration units? All right, so let's talk about mole fraction then. Mole fraction, which can be given by either this funny looking italicized X, or sometimes you'll see it referred to Greek capital or Greek lowercase letter chi. The mole fraction of a solution is the total number of moles of one of the components of the solution. Sometimes it's the solute, sometimes it's the solvent, divided by the total number of moles of all of the different components of the solution. Now, there are two things about mole fraction that are a little bit tricky. First of all, the numerator here does not have to be the solute. It can be any component of the solution. Kind of like when we did mass percents. We could calculate the mass percent of anything, whether it was a solution or of a compound, and we could investigate any component of that compound or any component of that solution and figure out its percentage. Same thing here. The other thing that we have to be aware of is that the total number of moles we have to find the moles of each component separately and then add them together. One of the weirdest but most common mistakes I see with this is we get told that we have 30 grams of one component and 50 grams of another. And to find the total number of moles, what I'll see some of you do is you'll turn it into 80 grams of solution and you'll figure out some way to figure out the total molar mass. And you'll use that to figure out the number of moles of solution there. Doesn't work that way. What you need to do is you need to figure out, okay, I've got 30 grams of component A. How many moles is that? I've got 50 grams of component B. How many moles is that? Figure out the moles separately, then add them together. You can't try to combine it all into one quick step. Doesn't work. Now, we're going to use each one of these concentration units in the other parts of the chapter. What we're getting after is something called a colligative property. What a colligative property tells us is that this is a property of a solution that is dependent only on how much solute there is, not on what the solute is. So what we'll see is that it is going to depend on the concentration value, not the identity. Now, all of these colligative properties have a direct relationship with intermolecular forces. The stronger the intermolecular forces are between the solute and the solvent, the more pronounced these properties that we're going to investigate will be. And the properties that we are looking at involve phase changes, which is what we'll see in these three here. And this will be the subject of the lecture on Monday and on the following Monday, because we've got that exam in between, and next Friday is not actually an exam day or a class day at all. But today, we're going to focus on a property known as osmotic pressure, which has a lot of biological implications to it. So to start talking about osmotic pressure, we need to talk about osmosis. Now, most of you remember, because osmosis was covered in biology when you were freshmen in high school, and probably some of your physical science classes along the way. If you've taken biology here, you've probably heard it talked about there as well. We're talking about the spontaneous movement of water through what is called a semi-permeable membrane, meaning that we have some sort of barrier that water can cross through, but other substances cannot. Your cell membranes are a great example of this. Water generally can pass through the cell membrane, other stuff can't. Now, there's a directionality to this migration. It always moves from an area of high concentration to an area of low concentration. And the concentration that we're worried about here is water, which kind of puts it in direct opposite kind of relation to how we normally measure concentration. It's all about the concentration of the solute. Well, in a solution that is high in solute concentration, it's going to be low in water concentration and vice versa. So osmosis is going to go from the higher molarity side to the lower molarity side. Or strike that, reverse it. Water is going to go toward the higher concentration, the higher molarity substance to try to dilute it. Osmotic pressure can be measured as, let's say that we have a semi-permeable membrane. And let's say that water is flowing across that semi-permeable membrane. What osmotic pressure would be is how much pressure do I need to apply to the one side of the semi-permeable membrane to stop water from flowing across. So if I've got water going from left to right, if I apply a pressure on the right-hand side, how much pressure do I need to apply on the right-hand side to keep the water from flowing from left to right? How much do I need to apply to get that flow to stop? We're not trying to reverse the flow. We're just trying to get the flow to stop. That's what osmotic pressure is. And we can calculate the osmotic pressure of a solution based upon two factors: the molarity of the substance, of the solution, and its temperature in Kelvin. Now, the other factor here, the capital R, that is something called the universal gas constant. We'll get more into that when we get into chapter 9. But we'll give you some values of it here that you can use. So the osmotic pressure is related to the molarity of the solution, the absolute temperature, and that value of R. So here's an example of what that might look like. Let's say, for the sake of argument here, that I've got a glass tube. That glass tube has a U shape. It is called a U tube. In the middle of that U tube, I've got this semi-permeable membrane in place. That semi-permeable membrane allows the flow of water to pass through in either direction, but the salt particles themselves are too big to pass through the membrane. On the one hand, I have seawater, very salty, brackish water. On the other side, I have a normal saline solution, kind of stuff that you would put your contact lenses in. So there's an obvious salt disparity. The left-hand side is way saltier than the right-hand side. And so what we will see is that the natural movement of the water is going to be from right to left. We're going to go from the side that is less concentrated, has more water, to the side that is more concentrated and has less water. And the net result is that if we introduce no influence whatsoever, there's going to be a disparity. The water is going to rise up on the one side and fall on the other. Osmotic pressure would be how much pressure do I need to apply on the top of this tube to get the water levels back to where they were, back to even. Now, there's one other factor that needs to be introduced and discussed here with osmotic pressure, something called the Van Hoff Factor. What the Van Hoff Factor discusses is the fact that we're looking at what is called total concentration. Now, we have to understand that for ionic compounds, the total concentration of those solutions is not going to be merely the molar concentration of the solute. We know that when ionic compounds dissolve in water, they don't dissolve into their individual little molecules. They break apart into all of their ions. And so what we get for a substance like sodium chloride is not a series of NaCl molecules dissolved in the water. What we get is a series of sodium ions and chloride ions in the water instead. Every sodium chloride molecule that dissolves gives us 2 ions in total. And so what that means for the total concentration is that, let's say I have a 1 molar solution of sodium chloride. Well, when that sodium chloride breaks apart, I end up having a 1 molar solution of sodium ion and a 1 molar solution of chloride ion. Put those two together, the total concentration is actually 2, not 1. That's the Van Hoff factor in play. Now, for substances that are not electrolytic, like ethanol, there's no breaking apart that takes place. And so the Van Hoff factor is exactly what the concentration was in general. Van Hoff factor is 1. The total concentration is exactly the same as the regular concentration. So if I take the Van Hoff factor I times the molar concentration M, that is going to give me what we call the total concentration. We can estimate I by looking at the ionic compound itself. So for the sodium phosphate here, I would expect 3 sodium ions and a phosphate ion. If I had a 1 molar solution of sodium phosphate, I would expect that because there are 3 sodium ions, the total concentration of sodium would actually be 3 molar. And the phosphate ion would be 1 molar. And the total, 3 plus 1, gives us 4. 4 molar concentration. That's what is referred to here as the theoretical value. Now, some of the example problems in your book will give you instead what is called the experimental value. The experimental value takes into consideration that, especially for some higher concentration stuff, we just simply run out of room to have all of those ions all floating around all over the place. And so some of them end up remolecularizing inside of solution. And that's why we see a slight dip off for all of those. Here's the rule of thumb. If the book problem gives you an experimental Van Hoff factor, use it. If they don't, assume that you can just break down the ionic compound into its pieces and use the theoretical value. As far as values of R are concerned, there are 2 really that we use. There is 0.0821 and there is 62.36. The difference between them is merely the unit of our pressure. So there are 3 common pressure units. There is atmospheres, which measures the pressure relative to the atmospheric pressure. There is millimeters of mercury, which is what you can measure on a barometer. And then there is torr, which is basically the same thing as millimeters of mercury. It just happens to be named after the guy who invented the barometer, Evangelista Torricelli. Now, all 3 of those values are on that equation sheet that we give you. So don't worry about memorizing any of them. Just understand that the use of one versus the other has everything to do with what the pressure unit is. So if we know that the pressure unit we're shooting for is atmospheres, we're going to use that top one. If we're looking at millimeters of mercury or torr, we're going to use that bottom one. As I said, this does have biological implications. Take, for example, your blood chemistry, which is a very complicated mixture of carbonate buffers and water and a whole bunch of other stuff. Now, your blood cells, your red blood cells, should look like that one in the middle. Circular dimple in the middle. Indicates that you've got good oxygen flow and you've got the proper amount of salinity. If your blood was taken from your body and put into pure water, osmosis would take over. Water concentration on the outside is greater than on the inside. Water starts to flow into those blood cells. They end up puffing up like a balloon. Can't be good for the blood cell. Water eventually can go in there to the point where it basically pops like a balloon if you put too much air into the balloon. On the other side, let's say that you take that blood, move it out of the normal system and into a system of salt water. There you have something called a hypertonic solution. Conditions outside of the cell are saltier than inside. Water flows out of the cell to the outside. Your blood cells shrivel up. Also, not good for their overall well-being. So, one of the reasons why we have to maintain a very pure kind of sense of what we need to put into our bodies, think about an IV bag. If you go to the hospital for fluids because you've been dehydrated or you've been sick, they don't just put pure water into your veins. They put in a saline solution. Why? Because your blood needs a certain amount of salt to it to maintain functionality. You put that pure water in there, it puffs up like a balloon and bursts, and that's not what you want either. So biological implications are high for these kinds of actions. Let's do an example of a calculation involving osmotic pressure. We are told that the total concentration of solute particles inside a red blood cell is 0.310 molar, and that it is at body temperature, 37 Celsius. What we want to know is what is the osmotic pressure of this fluid. Now, keywords here, we've already been told that this is the total concentration. Since this is the total concentration, we don't have to worry about the Van Hoff factor. The Van Hoff factor has already been kind of baked into that concentration value. What we need to do is do our calculation. Pi is equal to MRT. Our molarity is 0.310 molar. We haven't been given a value of R or a ending pressure. Let's use 0.0821 liter atmospheres per mole Kelvin. 37 Celsius, remember we have to convert that to Kelvin. 37 plus 273 is 310 Kelvin. So 0.310 times 0.0821 multiplied by 310 to three significant figures is 7.89. Now, why does this unit combination work? Moles cancel, liters cancel, Kelvin cancels. All that we're left with is atmospheres. So our unit here is atmospheres of pressure. So if what is being said about the concentration is accurate, that means that the osmotic pressure of your blood is just a little bit less than 8 times atmospheric pressure. So this is kind of the most direct calculation of osmotic pressure that you can have. Any questions about this before we move on? All right. Another application of osmosis is the process of reverse osmosis, which is used for most water purification techniques. Basically, to do reverse osmosis, you have to pressurize the water past its osmotic pressure. So to do that, again, you have to have a pretty good idea of what the concentration of the solution is. So in the case of what we had there, we'd have to have at least 8 atmospheres of pressure being applied to get the water to flow the other direction. Chances are pretty good we'd actually want considerably more than that so that we could actually get it to flow with any kind of speed as opposed to taking all day to get a cup of water. One thing about reverse osmosis processes, however, depending upon what it is that you are reverse osmosising, there's a lot of waste involved. If you're trying to do desalination, like taking ocean water and purifying it for drinking water purposes, you're going to find that a lot of that water ends up getting pushed out as waste, maybe as high as a 20-to-1 ratio. Now, you can collect that water and push it through again, but there is a efficiency issue that does come about when it comes to these processes, especially when you're taking very high concentrations and bringing them down. Because that waste, that salt has to go somewhere, right? So it ends up going into the wastewater and making it more salty than it was. There's one other application that we can use and kind of introduce it, and we'll do the calculation for it on Monday. Determining molar mass. One thing that we can do is we can more or less take this concentration business and flip it around on its head. If I know my osmotic pressure equation, I know that I can flip it around like so and turn it into molarity is equal to pi over RT. And from there, use this equation to figure out how many moles of the solvent there are. So that's kind of the end result of this. Is you can take substances where we don't know their molar masses, make solutions of them, measure their osmotic pressures because the pressures won't be that high, won't be so hard to measure, and work backwards through this, knowing how much solution you made, knowing the temperature, using the measured pressure to figure out how many moles of solute were in there, and comparing it with how many grams you added in the first place to figure out its molar mass. It's a great characterization technique, just out of time to talk about it. So this is where we will actually start on Monday.